Hi, welcome to a video tutorial from Robojax. My name is Ahmed Shamshiri. In this video we are going to design a Mosfet based full bridge motor driver with high side and low side with gate driver. I'm going to use the IR2101 gate driver. This will have full speed control, direction of rotation, and also I've implemented stop and braking feature in the code. I'm going to explain how the high side and low side is being driven. Then I'm going to explain the schematic. Then I'm going to show you the wiring diagram for the breadboard so we can implement the project on the breadboard and test it and place order online. And then I'm going to show you the wiring of the PCB and test our project. 50%. That was 50% on brake, and now so Mosfet is one of the best solutions to build an H bridge, but you need to use N and P channel MOSFETs and drive them properly so they work. One way to do it is using gate driver. I use this IR2101 and used all N channel MOSFETs. This is IRFZ44N, which are all N channel, and it makes the design much easier. And also the design that I've implemented here is that you can run even 3 volts motor or maybe 5 volts up to 24 volts. So in order to make this gate driver work with all voltages, I've used here a boost converter that gets 3.3 volts or 5 volts and converts it to 20 volts. Because gate source voltage is plus minus 20 volts, so it's very safe to supply up to 20 volts to the gate, and this way it's fully saturated and it acts as a best switch. And also this MOSFET has 17.5 milliohm RDS on. When drain source is turned on, the resistance is very low, relatively low. I've designed everything in PCBx EDA. I've drawn the circuit, then produced the PCB. I've made some correction later on the actual PCB on the Gerber file, but then I placed order using PCBx Service, and I placed order for 5, and they shipped it to me. And the product is perfectly working. It was my mistake to forget. This was my mistake to forget one of these chips to be connected to the ground, so I put this wire. I didn't need to reorder. Initially, I designed it with optocoupler to isolate it from Arduino, but there was some design defect because I made some mistake with the design, so I just eliminated and used it without any optocoupler. This space was empty. I incorporated a rotary encoder, which I have not used it in this video. I will provide you the Gerber file and also the schematic if you want to produce it and get the deal from PCBx. The link will be below this video in the description. Now let's understand how the DC motor is controlled. This is our DC motor and this is our battery. We just connect a switch in between the motor and the battery, either at the positive wire or at the negative one, but most of the time preferred in here and the positive, so we can turn it on and off. Now this terminal is connected to the positive, the left side is connected to the negative. And in this case, if it is connected in this configuration, let's say a certain motor is rotating at CCW or counterclockwise. If we switch the positive, which was before connected in here, now we bring it to this terminal, and the negative, which was in here, move it to the other terminal, the motor will rotate in the clockwise direction. Before it was counterclockwise, now it changes the direction of rotation. So we learned that if we change the polarity of the power to the motor, the direction of rotation changes. And here, for this motor, I'm connecting the negative to this terminal, and positive to this terminal. Pay attention. As you can see, it goes counterclockwise. Now if I switch it, connect it to this terminal, the negative is now here, the positive is switched. As you can see, it's going clockwise. Now the question is, why can't we just connect the motor directly to Arduino ESP32 or Raspberry Pi, whatever it is that you're using? The answer is that the microcontroller cannot supply enough power to the motor because this motor, even if it's 5 volts and the output is 5 volts, this will not be able to run it because the amount of current which is the unit is ampere is not enough. This will supply, for example, 10 milliampere or 15 or maximum 20 milliampere, but this will need 1200 milliampere connected directly, and we need something called driver, which gets the signal and amplifies it many times, and so we can control the motor. Let's see how H bridge works. This is our motor, the positive is connected to VCC, this is our power supply, battery, or whatever source you have, and this side is connected to the ground. This is a symbol for the ground or negative terminal. Now if we, in this case, let's say this motor is rotating in CCW direction or CW, clockwise direction, the positive of the motor is connected to VCC. Now if we change it, now the positive of the motor is now at the bottom and negative is at the top, which is connected to the positive. So in this case, now the motor will rotate in the counterclockwise direction, which we just explained. This is a bipolar junction transistor which has collector, emitter, and base. It has 3 terminals. This is NPN, but doesn't matter. I'm just giving you an example. So this transistor can be used as a switch, and I'm just creating a similarity between these. So one side of switch is collector, the other side is emitter, and base is where you push the switch. So you can turn it on or turn it off like that. We create a configuration like this with 4 switches. You see SW1 switch 1, 2, 3, 4 connected to the motor like this. This is called H bridge because it looks like H. So, and if we turn this switch on and this switch on, switch 1 and switch 4, you will see that the current cannot go here because this is not connected. So the current will pass through switch 1, passes through the motor, goes through switch 4, is completed to the ground, and as a result this motor will rotate, for example, in a clockwise direction. But if we turn this switch 1 and switch 4 off and turn on switch 3 and 2 at the same time, these 2 switches, then the current which before was coming to here, you see the VCC positive was connected to the negative. Now positive is connected through this because this is off, through this to the positive. This is now not connected, so it goes through the motor and exits from the negative terminal and connects to the negative. As a result, this will now rotate in counterclockwise. Before it was rotating clockwise, but now it goes counterclockwise. So using 4 switches, we can control a motor easily. And as I mentioned, instead of switch, we can use a transistor as a switch, so we can quickly turn it on and off and control the motor. This configuration also can be used for a break or quick stop, where switch 4 and 2 is turned on, and because the motor was rotating, it generates energy, and it slows itself faster. Or you can do it like this. So 3 and 2 is on because this positive just goes and circulates. There is nothing connected to the ground, or in this case nothing is connected to the VCC, so there is no harm, but it can stop the motor quickly. Now the problem occurs if you connect or if you turn on S3 or S4. You see the positive doesn't go here, it passes through these two and there is a short circuit, and oops, so the fuse will blow up, or maybe the wires, there will be fire or something. And the same thing if you do turn on switch 1 and 2 at the same time, the same thing will happen, and there will be fire, or if there is a fuse, the fuse will blow out. So this is how each bridge works. Now when we use a MOSFET as a switch, this is a drain and source, and we have to turn the gate high to connect it. When gate is low, the switch is off, and when the gate is high, the switch is connected, drain and source is connected, so this will act like a switch. Now, we can use the MOSFET here. This is just an example of 12 volts, and this side is called high side, this is called low side. The reason for the low side is that this is, when this turns on, this is like a switch, so this is connected to the low side or the ground, and when this gate is high, this will turn on, this line will be short-circuited. This has very low internal resistance or drain source turn on resistance. It's called RDS on. This is located on this side connected to the power supply. This is called high side. And the current will pass through and the motor will rotate. This is just in one direction. And we will have the same MOSFET in here and here when we go in the other direction. Because I just explained it. We are going to show you only this one. Now, the motor will rotate, let's say, in counterclockwise direction. In order to turn on a MOSFET, this particular MOSFET needs 2 to 4 volts between source and gate, the gate source voltage, which means gate must be 2 to 4 volts, let's take it average, 3 volts higher than source. So, and also when this one also, 3 volts, this gate must be 3 volts higher than this ground. So when we say higher than ground, then the 3 volt will work fine here and this will turn on. But the problem is this motor needs 12 volts. When the MOSFET is turned on, the 12 volt is coming here, so we have here 12 volts. So this 12 volt is on the motor, and this side is now 12 volts. Now, if this is 12 volts, then from ground, the gate should be the voltage of the motor plus 3 volts, meaning this is 12 volts and the gate voltage is, let's say, 4 volts, so 4 plus 2, this must be 16 volts. If it's 3, then it will be 12 plus 3, 15 volts. So this is 12 volts. Where do we get 15 volts? That is where gate drivers come in and it will supply. So we need 15 volts to turn this MOSFET on. And here, this is IR2101 connected to this MOSFET. I'm just showing you here. And we have high in and low in signal. When high in is high, then high out will be high, and this switch will turn on. The low in can be connected to the other MOSFET, which I have not shown it. So, and the input voltage comes, there is a capacitor, and this side is connected to one side of the motor, and this will drive the gate for us. And that's what we do in this video. And here is the schematic. On the left side, we have a boost converter that receives 5 volts. This can work even 3.3 volts, and it will convert it to 20 volts. So this chip is MT3608 with this inductor and then Schottky diode. We have a potentiometer that we can set the output voltage. Output voltage is here 20 volts. So we will connect a jumper here to turn it on and off for some test purpose. And then this is the power supply input that comes to these drain of these MOSFETs. We have 4 MOSFETs, IRFZ44N are high side, Q1 and Q3, and then Q2 and Q4 are the low side. All the Mosfets are being driven using this IR2101 chip. 20 volts that we generated here is coming to this chip, and then we have another chip. The chip has high N and low N, which is connected via 1 kilo ohm resistor to Arduino in this case, and the output, high out and low out. High out is connected using 10 ohm resistor to the gate of high side, and from the other one as well, the high out is connected to the high side, and the low out is connected from one side to the other one to Q4, and from this side it is connected to Q2. The motor is connected between these 2 points, between the source and drain of this transistor and source and drain of Q1 and Q2 and Q3 and Q4. The input has 5 terminals, 2 for one high and low input, and 2 for the other one, and 1 ground. This project that you are watching is produced using high quality products from PCBx. PCBx can produce your PCBs, or they can do full assembly PCB. At the moment, for each new user, they offer 10 PCBs for $1, or you can do full assembly of 10 PCBs for free. The process is very simple. You click on PCB code, upload your Gerber files, review your product, select the options in terms of quality of material, number of layers, thickness, and tons of other options, and place your order. You can draw your schematic by selecting the components, then design it the way you want it, preview it as a 3D model, once you are satisfied, you can click place order, either place order PCB or place order for PCBx of full assembly. If you select PCB, for example, you don't need to upload the Gerber file or anything. All the information that comes directly from the EDA, you will see all the layers of your Gerber file. You can also view it in 2D, and also you can preview the 3D of the PCB. Add it to the cart and place your order. If you wish to place order for high quality fully assembled project, click on order and order PCBA. The same as the PCB, you will have options. You have the option to preview it, preview the Gerber file, preview the 2D, preview 3D of your project, select the component based on the type and quality, and request for the code. They will contact you about the cost, or you can use the free assembly of 10 PCB option here. The link is below the video. You can click and place order. Now let me explain the code. We have defined here pin 9, 8, 3, and 2 for pulse width modulation. This is the high N pin. Pin 9, the low N1. So this was high N1 and low N1. That's for one chip, 8 and 9. Pin 9 must be the pulse width modulation enabled pin. And then pin 2 and 3 are for high N2 and low N2. Pin 3 must be this pin, high 2, must be pulse width modulation pin. And these are the pins that labeled on the actual breadboard. So the label that we have here will match the code that you see. So pulse width modulation 1, and this is pulse width modulation 1, enable 1, pulse width modulation 2, enable 2. These are on the breadboard, on the PCB. Do not change this. We are defining clockwise and counterclockwise as 0 and 1. And these are the prototypes of the functions that are at the bottom of the code. Inside the setup, we initialize the serial monitor and pulse width modulation 1, enable 1, pulse width modulation 2, enable 2. Using pin mode, we define them as output. And then inside the loop, this is how we call. If we want a motor run at clockwise and 100%, we just say motor clockwise 100%. And this is the amount of time that we want a delay or some other action. So the motor will run unless you have a delay, it will not run. So this delay is keeping it running for 5 seconds and then break. If you want to break, just say break, open close parenthesis. So calling this function will break. And here it says break for 3 seconds. And then we say run the motor in counterclockwise at 100% for 5 seconds. And then stop. Break is to bring the motor quickly to stop, and stop is just coasting, turning the power off, and the motor runs until it will stop. And then this is saying that run the motor at 50% at counterclockwise, and then break. This is just a loop for learning purpose. We initialize I from 0 up to 100. So this I changes here. We say motor clockwise I 0, 1, 2, 3, it goes up to 100%, and every time we have 100 seconds delay. So this is incrementing because it's plus plus. This is decrementing it. This starts at 100% and it goes up to 0, and then break. So now the stop is just turning low, 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 and then high. As you can see here, this also could be. But break is very important. For the break, as I explained it, we have to have this pulse width modulation 1 and pulse width modulation 2, both of these high, and the other two should be low. This will cause the motor to break. And this is printing, by the way. If you do need it, because it uses some resource, just comment this out, and it will not be displayed. And then this is the motor that we call. This is the direction, and that's the speed. And then we, using this map, we convert the speed, which is from 0 to 100. We map it to be value from 0 to 255, which is used by Arduino here. And then this is just printing the text, and we check if the direction is CW. Then we turn on the motor like this. So pulse width modulation 1, enable 1 is high and with a speed, and the other is low. This is the second chip. But if it is CCW, then the top is low, the bottom is high and speed. This was the top, high and speed, and low was 0. This was a full explanation of the code. And here is the wiring for breadboard. I've used 2 breadboards because it will be too cluttered. Still, I have 5 volts here from the left side. The 5 volt is coming to this point where it goes to this module to convert it to 20 volts. This module, I'll provide you the link if you want to purchase it. And because I did not use that ground, because ground is used this way here to the breadboard. And then all the inputs, pin 8, 9, 2, and 3, they all come through 1 kilo ohm resistor and then gets connected. The most important part is to remember is this black wire, because if you do all the wiring, if you don't do this black wire, the motor will not run. Then the battery. The battery can be even 5 volts, 3 volts, up to 24 volts, because the operating voltage for this because the capacitor that I use is less than 24 volts. So if you want to use higher voltage for the power supply, that's fine. Even higher voltage will work fine. And then these diodes are, this is IR2101, and then these are 10 ohm resistors, 1, 2, and 3, and I believe there is one more. Yeah, it's below this. After this blue, there is one more resistor. I have covered it. I'm going to fix it when I upload it. So you can do the wiring from this as shown here. I'll provide you this wiring in the resource page for this video. Here is a setup and wiring. Everything is ready. I have the power supply that is connected, which is power supply. If I measure the voltage, around 9 volts, 9.2 volts, and then it goes to this boost converter, which is, I use this boost converter. This side is the input and this is output. It receives maybe 2-3 volts any voltage, so 5 volts, and we are getting 20 volts. I have covered it with tape so it doesn't make short circuit here because it was already exposed. On the breadboard you can see this is my 20 volts. It is 5 volts. So now the code is running. If I open the serial monitor, we see that this is now running clockwise and counterclockwise. The motor is not connected, so I'm going to connect the motor. Now this is break, and then let's see. That was break, which was quick. This was stop, not break. So it works perfectly on the breadboard, and currently the amount of current is 1.24 ampere for this at 9 volts. Now let's say your order is completed. You can just click order. PCB is just a PCB. PCBA means assembly. So let's click this. And here we will see our order. All the information is here. Part number, information, as you can see, for 5 pieces. Lead time 8 days. Part cost $27. PCB cost $5. Global shipping $8. And here are the other settings. The type of PCB. number of layers, the thickness, board type, and the rest of the solder mask. Whichever color you want, you can select it. I'm going to go with green. So this is the 2D view of what we see, and here the 3D. And it doesn't show the buttons. So now check out. So after placing order, the package has arrived. Wow, multiple layers of protection. So each package is protected, making sure that these capacitors do not bend. There is a PCB. On this side we have a terminal for, it can work even with a 3.3 volts or 5 volts. So there is an input with 5 volts, and then we have the power supply. This is the same power as your motor. So if your motor is 12 volts, connect 12 volts. If it's 24 volts, connect 24 volts. If the motor is even 5 volts, connect 5 volts here, and the motor will be connected at this side. Then we have the data input on this side, where this will be connected to your pulses modulation and signal control, like Arduino ESP32 or Raspberry Pi if you wish. And then we have 4 motor. This connector, this is a potentiometer where we can set the voltage. The 5 volt is coming using this boost converter. It converts it to 20 volts, and the middle pin is the output. This is a placeholder for the rotary encoder, in case if you want to control the speed of motor or whatever using the rotary encoder, and with the required resistors already included. I try to put some information here for the voltage and current. These are the gate drivers, IR2101, and then we have 4 Mosfets. These are IRFZ44N, all of them. These are from one side, high side, low side, and this is for the other side. This is a high side and low side. Because the high side is getting hotter, so I put them on the side. If needed, we can include larger heatsink, but here also we have some room for a smaller heatsink. This rotary encoder I have chosen for this motor driver. Let's just see if it fits. Let's put this knob here. And I've connected my multimeter at the input. If I connect this, we see 5 volts. This is a wire for the multimeter. And I'm going to connect it to the middle terminal here. This is the output voltage from this boost converter. Now this is increasing. So I set it to 20 volts. 20 volts. So the output is set to 20 volts. Now, because we are not going to use the rotary encoder, and in order not to confuse you, I'm simply covering this, so this will not be used. Now I'm going to connect this terminal and this terminal, the middle, to this side, so we can have 20 volts supplied to the gates. Now has been connected. And here for the wiring, I've connected 5 volts to this part. 5 volts is connected to Arduino. This is getting 5 volts and converting it to 20 volts. And then these two middle wires, these are connected to my power supply. The last two wires are connected to my motor. I'm going to connect this later. For the Arduino, we don't need this ground because I have a ground, but I already connected it. So the first one is connected to the ground. Orange is connected to pin 2. Yellow is connected to pin 3. Green to pin 8. And blue to pin 9. And here is a demonstration. The motor, everything is ready. As you can see, Arduino also shows the code. Currently it goes from 0 to 100% and from 100 back to 0. And as soon as I connect it, I'm going to explain it. So let's connect the motor. And I'm going to reset it so it goes. So first it goes with high speed clockwise and then brake. Brake is to stop it very quickly. Let me connect it and reset. Now it goes. It was brake. It changed the direction and also it stopped. It just went slowly. And now it will go with a slower speed. Let me do it again. So the brake and then counterclockwise. Now it will speed up slowly, 50%. That was 50% on brake, and now slowly increases. %, and now decreasing. And brake. So this was a demonstration. Amount of current was 1. Let me check it again. How much was it? 100%. I'm restarting it. The voltage is 12 volts. So at 100% pulse width modulation, it was 1.7 ampere. And these transistors are very cool. They don't need even heatsink for 1 or 2 ampere. Here, as you can see, This can go up to 49 amperes. This is huge. Of course, it needs huge heatsink. More than 2 ampere, you need to put some small heatsink. But if you want to go 5 or 10 ampere, you need proper cooling. Thank you for watching. This was a full bridge using Mosfet and gate driver. The PCB have been produced in PCBx. They have excellent deals at the moment. The link is below this video if you want to place order. Make sure to thumb up the video and also subscribe to my channel. I appreciate it.